So this section is about non-idealities in motion control. So very important aspects that actually make the difference in practice, but that you cannot find in school books. So, or at least not all of them. In particular, as we said, we have our encoders to measure the joint positions. And these encoders are spitting out a digital number that, depending if they are relative encoder or absolute encoder, this number will be an absolute position or a relative position to an initial, to the startup moment. In case of the number of bits of this encoder determines the resolution, that is the accuracy of the encoder, in the minimum angle that the encoder is able to discriminate. For example, a 12-bit encoder is a quite crappy one. We used back in 2010 just to get the home position. And in this case, you divide to find the resolution 2 pi by the 2 to the 2012, 2 to the power of 12, which is 4096, and this is around 0.09 degrees. So if you close the loop with this encoder, it's not that accurate, but it's not only that. The encoders, for example, people say that let's sample as fast as you can because it's nice. With encoders, it's not necessarily the good thing, because if you think about the sampling time, the sampling interval, if you get when you as we said, you compute the velocity differentiating with first order differentiations of the position. Whenever the sampling interval reduces, the quantization noise increases. So you see your velocity signal is like a bunch of spikes. You have many spikes, and especially you have one spike for each change in position. And this spike will be higher according to the lower sampling frequency, to the faster sampling frequency. In addition, there is a minimum speed that you can measure, and this not many people are aware about. So let's say that to discriminate the lowest speed, you need to see at least one change of count. This means in the case of our 12-bit encoder, 0.09 degrees, divided by the sampling interval, which is 1 millisecond, let's say. And in this case, you see that you get the minimum speed you are able to discriminate. It's 90 degrees per second, which is quite high. So either you increase the accuracy, so you increase the resolution, and you reduce this number, or you sample lower frequency. The second element that is not modeled mostly in robotics is the friction. Friction can happen, for example, in the sliding parts, for example, in the piston, between the piston and the cylinder, or in the bearings. Whenever you have a rotational joint, you have bearings that have spheres inside, and this create rolling friction. And the common feature to all the kind of frictional forces is that they always oppose motion. And the most that's used model, whenever it's used, people using robotics is the Colombian one that separates the friction into three terms, let's say. One is the Coulomb friction, which is it's constant. Viscous friction, which is velocity dependent, and the stiction. Stiction, it's like Coulomb friction, but whenever the motion is stopped. And normally stiction is a bit higher than the Coulomb friction. So the friction force is always, the Coulomb law says that the friction force is always tangent to the contact and is proportional to the normal force that is applied. And the proportionality is related to the value of the friction coefficient mu. So the tangential force is proportional to the normal force times mu. And the mu, the friction coefficient, depends on the two materials that are in contact, while the tangential force is independent of on the speed of sliding for the Coulomb term. The stiction instead is called the breakaway friction, and it's like, as I said, Coulomb friction at zero speed, and it's slightly higher than the Coulomb friction. So we see here the Coulomb friction changes sign when the velocity is changing, and in here at zero speed we have the stiction, which is slightly higher, while the viscous friction is proportional to the velocity. If we sum up these three things, we get a plot like this for the whole friction forces, and this connection here is called the Steinbeck effect. So it's the fact that the stiction is bigger than the Coulomb friction, and so we have an initial a positive slope in here rather than here, and this is as a destabilizing effect. And this is responsible of the famous stick and slip phenomena, that the robot starts to move and stops and starts to move. However, in this course we completely neglect stiction, we just consider Coulomb friction. And an important point is that Coulomb friction Coulomb law can be interpreted as a friction cone. This is if we expand the previous idea that was on a linear direction on two directions. So this is the contact force that will have an x, z and y component. And we see that defining that the friction force, tangential force, is related to the normal component, it's like telling that the friction force should stay inside a cone, where the base of the cone is the maximum allowable value of the tangential force proportional to Fz, the Fz component. So if the force F is inside this cone, we're sure that the tangential force is lower than the mu Fz, and there will be no slippage. If this is touching the cone, then a slippage motion starts to occur. And as Coulomb law says, this whenever during the slippage, the force will be lying on the cone continuously, and it will be constant. So whenever a slippage starts, the forces stay constant. Inside the cone, the force can do whatever it wants, and there is no slippage. In particular, this angle is the arctangent of the friction coefficient mu. So the size of the cone depends on the friction coefficient. On ice, for example, you will have a very, very thin friction coefficient. While on sandpaper, you will have a very large one. That's why when you walk on ice, we try to walk like this way, trying to apply as much vertical contact forces as we can, because any tangential component will make us slip. Identify friction and compensate for it, it's tricky. It's difficult. You saw that discontinuity. You might have to check the motion velocity and apply this Coulombian force. at the friction damping, the viscous friction compensation. And what people do, what we do actually in our lab is to have, for example, we have an hydraulic actuator here that is composed of a cylinder and a piston, and you have a big friction in here. So rather than measuring the pressure, the force that you apply to the joint as the hydraulic pressure, we measure after the actuator with a load cell. A load cell is a force sensor that allows us to really check whatever the force we are applying, so the torque to the link. And this way we don't care about the friction because we close the loop with a torque control, for example, in here, and the controller will automatically take care of this. While if you're using electrical motors and you are controlling the current, for example, because you want to apply a torque to the joint using the current, then you need to model the friction, because the current is before the, I don't know, the bearing friction of the rotor. Because we should have an electrical motor. You have the coils, you have the current, but then the actual magnetic field is making rotating the rotor, which is this one, and there are bearings here. And here you will have friction. So you control the current, but you in the end, whatever it gets to the link, this torque, it will be the current one. Let's say it's proportional to the current minus the friction torque that's happening here. Another point that is important is the backlash. Backlash is whenever you have clearance of motion due to gaps between mechanical parts. For example, the teeth of a gear wheel. So you want to transmit motion, and there is like a little play between the teeth, and then you move the first gear, and then before the second gear starts to move, it does like a free motion. And this means that you have discontinuity into controlling the force and the torque. And this creates instabilities if you have a torque loop, for example. And the only way, and this instability shows up as limit cycles or vibrations. The only way to deal with this, I'm sorry, is doing a good mechanical design. So try to use conic fits, spiral that enable to reduce the backlash.
But aren't there any works like modeling it in software and trying to compensate for backlash specifically? Are there any specific works in the literature that does this? No?
I mean, there are, but
very minimal.
We were not. I mean, we were able to get rid of this with a good design. Some people, they do dithering. They continuously move back and forth to keep the contact with the two gears, but it's not ideal. There are all hacks. Unfortunately, it's something that there are some works on that certainly, but we prefer to do a proper mechanical design to get rid of this. And still, we have some backlash, and you hear vibrations sometimes coming out. Another point, especially that whenever you have an hydraulic valve or motor driver, it's the dead band. The dead band, let's say, it's in the case of an hydraulic valve, is whenever you have an overlap. So let's say you have the spool. So pressure, tank, this is a valve works like this, chamber A, chamber B, so you have our hydraulic cylinder with 2 chambers, and we want to move the valve to the right to connect pressure to chamber A and B to tank, and the other way around to shift. So whenever there is an overlap, you will have an area of the input signal that has no flow. So it's like you have 0 gain here. And so whenever you want to change the direction of the flow, you need to take this deadband into account, because otherwise you have a non-continuous contraction.
Overlap of what?
Of the spool. So an underlap is like this. This is an underlap. So you have always some flow going, even if whenever it's in the middle position. And an overlap it's the other way around. Whenever it's always close in the middle position. And critical overlap is whenever it's exactly touching the edges. So it's the best thing. It's what we have in the move valve. That's why they have a very high bandwidth in opening and closing. So the first thing you can do, the only thing you can do with the deadband is to do the opposite. So you apply a control action that has this behavior, and this is what we were doing back in 2010 before using move valve, because that valves, they had overlap, the first one we used. And the same thing, deadband, you could have, for example, in an electrical motor, whenever you have a driver and you know that you need to apply some voltage to have at least some voltage to have a certain start to increase the current. So there is a minimum voltage drop due to the diodes in the book converter that they the converter that creates. You need to create a certain voltage drop to start to have the current increase. So it's the same thing. Another point element that is mostly used in electrical motors are the gearbox. So in hydraulics, let's say we have a high power to density ratio. So it means that with hydraulics we are able to, with a piston that is 1 kilogram, we are able to apply high forces and also high velocity, which means high power, so that in 1 kilogram we have a high power density. With an electrical motor, no, because an electrical motor is able to apply, give a high force, but then due to the back MF, whenever the speed increases, its torque, its force decreases. So if you want to go fast, if you want to have a small motor, let's say, that runs fast, and you want to achieve a high force, then you need to have a gearbox. And the gearbox has the effect to amplify the low torque of an electrical motor and allow you to use small motors, because if you increase the torque size of a motor, you increase the size of the motor, you increase the weight, and then you are going to have a problem, because in legged robots you need to carry around your weight. So if you have a heavy motor, it's not good. So the most, let's say, famous one is harmonic driving gearbox, and you see that the gearbox changes the rotation of the motor. Let's say this is the rotation velocity, and this is the link velocity. And the way this change is done is called a gear ratio. So let's say if we have a 100, it means gear ratio. It means that the motor spins 100 times faster than the link. And if you do a power balance from motor side and link side, you see here that the power is the angular velocity of the motor times the torque of the motor. On the link side is the angular velocity of the link times the torque of the link. And you see if these are related, you have a reduction in speed whenever you go to link side, but you have an amplification in torque whenever you get to link side, because the power balance needs to be the same. You don't create power from whatever. But if you look at the inertia, and we write down the inertia of the motor reflected to the link. So we, to compute the inertia, we do the torque of the link divided by the acceleration at the link. We replace these quantities, so we find that the torque at the link is the torque of the motor times the gear ratio, while the acceleration of the link is the acceleration of the motor divided by the gear ratio, because the acceleration and velocity, they have the same transformation ratio. And we see here that we obtain tau m divided by the acceleration of the motor, which is the inertia of the motor, times n squared. This means that the motor inertia, the rotor inertia, that is at the rotor, after the gearbox is amplified by n squared. And you need to take care of this in your model, because now in your end, your link inertia will be the inertia of the link itself plus the reflected inertia that is coming from the rotor of the motor. And if n is high, you need to take it into consideration, because it will affect the time response and the transient. Ideally, the link inertia, so what people do to tune the PD controller or the controller, if they don't want to make things complex, they do a geometric average of the minimum inertia of the leg retracted and the maximum inertia of the leg extended, and then they consider the inertia of the rotor that is constant. And here there are some.
I'm sorry, could you repeat where that averaging is used?
Whenever you want to design a controller, and let's say a decentralized one, and whatever we did between the PD gains, let's say, and you don't want to a single number of inertia, so you need to decide an average number for the inertia, and your leg inertia is changing, because if you consider this joint, for example, if I want to tune the PD gains for this joint, so we said we need to know the inertia from CAD, and then we set Kp and Kd to have critical damping. But if the leg is completely extended, you will have a certain number of inertia, while if it is completely retracted, you have another number. So CAD suggests to do this geometric average and take the minimum value and the maximum value, and then if you have a rotor, electrical motor, you add the rotor part. What people do, especially at MIT, they try to go for a smaller n. So this means their n, they don't go beyond 7. Okay, this way they have.
Here's the teeth of the gearbox, right? The number of teeth in the gearbox, or
this is the gearbox ratio. Okay. So usually in the past we use 100 and 100. Now the new trend are to use lower gear ratio. Why? Because we are able to this way to have bigger torques. to have faster motion, so we don't reduce the velocity of the motor. We don't lose much velocity of the motor, and to solve the problem of low torque, because now the torque of the motor is only multiplied by 7. They do over voltage, so rather than use 48 volts to drive the motor, they spike up to 180 for a short amount of time. So ideally, you can extract any power from your motor. You can have a motor like this size, and you can ask to deliver 3 kilowatts. You increase the voltage. What is the problem? The problem is that if you apply this voltage, the current increases, and you have power losses due to joule losses in the coils of the rotor, and these joule losses are becoming heat, and this heat, proportional to the square of the current, will make the temperature of the coil increase until melting them. But if you take care of this and do this in a smart way, this means you apply, I don't know, the 180 volt only during the stance, and then during the swing you go to 0. Their current starts to increase, but doesn't have time to reach the melting temperature, and then it goes down. Then it increases, it goes down. So impulsively you can extract a very high power over voltaging them, or you can liquid cool the coil. You can reduce the temperature, extracting the heat. And this way you can have a small motor giving high current, high torque to the link, and also high speed.
But I mean, they showcase this on what kind of a robot?
Cheetah.
Okay.
Yeah.
But then the battery usage was very minimal, right? This was only for the experimental purpose that they showed, or was a practical deployment?
No, they deploy all the motors. They deploy an actuator like that.
So in the case where we apply such high voltages, we are obviously training from an external power source, right? If we want to go wireless and something like that, and
no, you can
usage time of the robot becomes way less.
No, they have batteries. You can get them from batteries.
Okay. No, I meant to ask. This reduces the usage time of those batteries, right?
Yeah. Depends. If you do a smart way with a book, I don't remember the name, voltage boost. You use the PWM. You don't waste energy to increase the voltage, and you consume the same power that you would consume. Actually, you're giving the high voltage only for a short amount of time, and if you compute the integral, which is the power of the torque or time, or times the voltage, it maybe is not a big power. Whatever you waste, you extract from the battery. So you use the high voltage only whenever you need the torque. So if this is just whenever it's touching down and it needs to push to decelerate the mass, and maybe during the swing you set it to 0. So or here the power is very low. So I think they managed to work for some, so even 1 hour. I don't know how much is the duration of the battery, but it's a good way of doing things.
Yeah, that's very good.
Okay. Yeah. Now let's go to start to introduce the interaction with the environment. So here we have we talk about the joint motion control. We talk about how to control it and different strategies, and how to solve possible problems, practical problems in the measurement and in the actuation. And now we want to see what happens whenever this kind of robot they get in contact with the environment, how to model the contact, and see how the dynamics changes because of the contact. So if we see a fixed base robot, again we are talking about a fixed base manipulator that is entering the contact with the end effector in one point. Let's say there is a wall here. You see that there is a force that appears, and this force enters in the dynamic equation that we wrote before with a Jacobian transpose, where the Jacobian is computed for the end effector point. And it's computed as the partial derivative of the four kinematics of the position of the end effector with respect to the vector of joint angles. So we see that also Jacobian is position dependent, depends on the configuration, and it will have different size depending on the number of constraints that the contact has. Think about a point contact. In this case, like the Lego high cube that is touching the ground. In this case, you are constraining the x, y, and z motion. You prevent the penetration of the table, and so you have only linear forces, linear constraint contact forces, and you have kinematic constraints. While if you have the foot of workman, that is a flat foot, you are constraining. You have a contact surface, so you have 6 kinematic constraints because we are constraining, yes, the 3 linear forces, but also the moment about the 3 axes. And the size of the Jacobian matrix will depend on this number of the type of constraint. And as columns, the Jacobian matrix will always have the number of joints. So whenever there are multiple contacts, we just sum up the Jacobian for each contact point. So let's say we have a robot contacting the environment in different points. A humanoid. And he's contacting here, contacting here, contacting here. And for each force you need to compute the Jacobian of each end effector. You sum them up. It's super nice. You can even stack them in a big matrix, big Jacobian matrix, and putting all the contact forces together. Now, what are the ways that contacts are modeled in the robotics community? There are two main ways. One, it's rigid contact assumption. That means that the position of the contact point does not change in an inertial frame. This is the inertial frame attached to the lab, and you know that if you have a 1 foot in contact, the position will be constant in that frame. This doesn't mean that it doesn't change. It will not change in the base frame, for example, because the base is moving. So we always define the contact point position about the work frame, and saying that the position doesn't change is equal to saying that the velocity is 0. This can be using the differential kinematics related to the joint velocity this way, or also that the acceleration is 0. And if we differentiate this, we get this other constraint written at the acceleration level, relating joint acceleration and velocity. And this means that there is 0 acceleration of the contact, because there are holonomic constraints. This brings to this, and we can get this from integration. So if we replace, we work out q dot dot from this equation, this constraint, the contact constraint, and we plug it back to the dynamic equation, we can get an expression to estimate the contact forces without the need of contact sensors, just using the model of the robot. So if you get q dot dot equal to j minus 1 j dot q dot, and we have q dot dot plus h equal to tau plus j transpose f like this here. We get m j minus 1 j dot q dot plus h minus tau.
There is a negative sign.
Ah, yes. Sorry. Okay. J transpose f, and we can work out f as J transpose sorry, we multiply J minus transpose because we bring this to the other side. 2 minus J dot Q dot plus J minus transpose H minus tau. Okay, this is called the this can be rearranged this way. This is relating the force to some and effector acceleration. So what we multiply for an acceleration that we get a force. What is the quantity that if you multiply for an acceleration you get a force? Inertia. Okay, in this case the force is an end effector force, so this will be the inertia seen at the end effector. We call it reflected inertia, the operational space inertia. But we will see in detail afterwards in the next lecture how does it look like. The problem of this approach that it's cool because we measure the torque in essence from our sensor. We have torque sensors. We compute the bias because we have the encoders, so we can get position and velocity. Again, we can compute the Jacobian derivative because we have position of the joints. We have a velocity here measured. The mass matrix is joint dependent, so we have the position of the joint, Jacobian again. We know everything, measuring actually position, velocity, and torques. And we can estimate the contact forces without having to use a contact sensor, a force sensor at the end effector, because whenever a legged robot is walking, the impact are very high. And if you think about put an ATI 6-axis force sensor in a robot that weighs 100 kilos, you will break it soon.
So, in the case of absence of torque sensors, could we replace tau with computer torques or something like that, just using the model information? In the absence of joint torque sensors.
In the absence, no, because you need the torque, an estimation of the torques for that. Because the dynamic equation has three things: acceleration, contact forces, and torques. And from knowing two of them, you can get the other one. But in that case, you don't have torques, you don't have forces, you know what's the acceleration, but you do you cannot do. But the problem of this approach is that it's the model dependent. So if you have a model error, for example, you think your robot weighs 80 kilograms and instead weighs 70, then you get an estimation error in the contact forces. In particular, if you have a torque offset, also you can have an error. What we see whenever we have torque offset and the robot is in the air and we estimate the forces this way, we see that there are some residual contact forces that are fake, that are due to the torque offset, because the torque should be zero. It should be just equal to the gravity, but actually there is an offset, so it shows a force. There is here a nice analogy to an optimization into the optimization field. Let's say that the contact forces can be seen as the Lagrange multiplier that enter the dynamic equation to enforce the contact constraint. So we have the constraint dynamics of the robot floating in the air, let's say, and whenever there is contact, the force that is in there, it's the force needed to make this happen. So you make the end effector acceleration go to zero. This is a nice thing I found out a while ago.
So, just curious, so I do not know much about the optimization thing, but then the torques are basically considered as a dual variables to the accelerations. Is that why this analogy is drawn, or to have some historical perspective?
Dual variable of the acceleration, what do you mean?
No, I mean, usually the Lagrange multipliers are called as dual variables.
Ah, yes.
So in this case, the force space is a dual space for the motion space. Is that why this analogy?
Yeah, definitely for that. We'll see kinetostatic duality afterwards that it shows this. Yes, this definitely a good point. The other way of modeling contact in robotics is using soft contact model. Sorry, soft contact model, not forces. This means assuming that the robot is not infinitely rigid, but there is a certain compliance, and this compliance makes appear the contact forces that will be dependent on the penetration in the environment of the end effector. So if you think about the initial, the point in which the end effector touches the environment and the current position of the end effector whenever it's penetrating the environment, then using a linear spring and damper model for the environment, we can compute the contact force using the spring damper model, knowing the penetration inside the environment of the end effector. And you can use this force in the equation, but it will be defined by his own algebraic equation. Of course, this spring damper can be three-dimensional, so they can create a 3D contact force, or even like 6-dimensional if you have the torsional part as well. Yeah, I would say.
But you need to measure the penetration somewhere.
Yeah, that's a problem that we faced with the whole body controller on soft terrain. To measure the penetration, you need to use a Vicon system that was estimating the position of the robot in the world, in the inertial frame, and then with the forward kinematics we could see the location of the foot, and then at the touchdown we were starting to measure the penetration, but you can understand it's not really ideal because you have errors due to the deflection of the leg that are errors in the forward kinematics, because you think you put the foot in a position, but because of the flexibility, when you put the weight of the robot on a leg, the leg slightly deflect, and you can have 1 centimeter accuracy, for example, in the location. Then you are also adding up errors due to the Vicon system that has an accuracy of 1 centimeter, so you can have an accuracy of 2 centimeters. So you understand that in a rigid terrain, 2 centimeters of penetration, it would be the maximum penetration you can have, or the penetration is way lower. So this way of doing things is not really ideal. It will be, you will see in the second part of the course, it will be good whenever you do optimization, because this kind of model, they are smooth, they have no discontinuities like the rigid model assumption. So there is no, the dynamic is not hybrid, it's always the same. It's not switching. And this, from the optimization point of view, it's advantageous. But they can become stiff. So especially if the Kc variable is very high, then you get a stiff differential equation, and this can take time to be simulated and also to be used, difficult to be optimized.
So mostly for controlling a real robot, we should use the rigid contacts.
Yeah.
While for simulating it's probably better to use the soft contacts. Can you provide us some examples of calculations of the XC with respect to the word? Because I found them in some, let's say, in literature, but I didn't get too well how to compute those positions. Because you said the XC point is fixed with respect to the inertial frame.
Yes.
But it's not fixed with respect to the... So you are mostly saying, I know where my robot will put his feet. That's what you mean? Or it's just like, okay, the XC vector is just, let's say, a Z vector, and it has just the Z component.
I'm not sure if you understood properly, but this opens up to a very important remark that is whatever we can measure on the robot is like the relative position of the foot with respect to the trunk.
Okay.
So, so let's say this is one leg with 3 joints, and we can measure this vector here through the encoders. So we can measure the position of a contact in the base frame. But then, to get this in the word frame, we need to have somebody that tells us how this point is moving in the space.
Yeah. Okay.
And this is, in robotics, is usually done from a state estimation algorithm that it's a Kalman filter, in essence, that fuses different inputs. Normally some inputs are due to the gyroscope, that it's in the IMU, the inertial measurement unit. You have measurement of the angular velocity. Then you have odometry. So the encoder themselves can be used. If you have 2 feet on the ground, you can compute the orientation and position of your base, of your center of mass, using the measurement of the feet that are in contact. Of course, if you have one point foot in contact, you're not able to do much. So this will be dependent on the contacts and how stable are they. Because if you have one foot and the other one sliding, and you get information from both of them, then you get a drift in the estimation of your base velocity. Then, okay, IMU, odometry, the visual flow. So you have a camera, let's say, and you see features, and these features they change from one frame to the other, and you know the motion from the feature, or how the feature moves. You know that you are moved. So this is a visual flow. Then you have a LiDAR, which is a scan matcher. And normally you have a laser, and you use that to correct the position. And from all this stuff, you get the position of the base in the warframe and the velocity of the base in the warframe. This is your state estimation. But this is really can be prone to drift. I mean, there is a whole bunch of research in the community only to develop a low drift state estimation. And we managed to get some results, some important results in that, but it was very hard. It was many years of research. So whenever you do things in practice, try always to do use it to define the problem, to define the optimization, considering the base trajectory with respect to the base. Unless you don't replan continuously. In that case, you continuously move the board. You can reset, do that reckoning. You reset the board at the beginning, and then this is the trick in essence, to avoid the accumulation of error or the drift, the state estimation. Okay. Now I would like you to introduce the lab of the first lecture. I don't know if you have your laptop here and managed to run the virtual machine. The first lab so yeah, let me know if you manage to run the virtual machine. So in the virtual machine, the robot control folder, there is a folder with the description of the lab. That is in essence asking you to do some exercises. One exercise is to generate a sinusoidal reference and for two joints. So I show you what is the robot we are talking about. We are talking about UR5 robot. So So it's a robot that this is the base. Let's say you have a shoulder joint, then you have a shoulder, another shoulder joint in the vertical plane. We have an elbow joint, and we have the free wrist joint. So in essence, we have 1, 2, 3, 4, 5, 6 joints, 6 degrees of freedom robot. So with this kind of robot, we should be able to control both the orientation and the position of an end effector frame that we call 2-0. Actually, it's not called 2-0, it's called in another way. You see here the links are in red and the joints are in black. And these are the names. Unfortunately, I didn't put this into the folder, so but we do soon. And if you look at the lab, I created a Python code that you can run Spider. Just to show you how it works.
Can you zoom when you're on the code?
See? Okay. I was running the lab without the solutions. I should run the one with solution just to show you that works. And so in this IBIS visualization, you can see the trajectory controlled by the controller that I designed following the references, sinusoidal reference for these two joints. So looking at the lab requirements, the first exercise is to define a sinusoidal reference generation for the second and the fifth joint at 1.0 to 1.5 Hz frequency with amplitude 0.2 and 0.4 rad. And after 3 seconds, stop the sign and give a constant reference. Then, second part is to do a step reference generation and implement different strategies. The joint PD control that we saw, increase the gains of the joint PD control to see that the tracking errors reduce, but you have still steady state errors. Then implement critical damping joint PD control, see that there are no overshoot in case of step input reference. Then add see how behaves joint PD control with gravity compensation, and see that the steady state error goes away. Then add the feed forward turn and see that the tracking even within the transit increases. And then implement the whole inverse dynamics, showing that the tracking is good even if you reduce the values of the PD gains. And then add an external, reduce the damping of the attractor together with the PD, the inverse dynamics, and see that the tracking is still good because there are no coupling due to the joint in motion. And then try to add an external force and see that in that case the inverse dynamics also has a tracking error because there is an external force applied. So yeah, in essence, you can see this is the code. There is one config file called x1 conf, wherever you can set the time, the sampling time of the controller, the duration of the sine. You can slow the motion if you are too fast with the slow factor, and define the frame name that is called e-link, and the factor link. And then you can set the proportional and derivative gains. And these are the parameters for the reference sinusoidal trajectory, amplitude, the frequency, and phase shift, and the initial values. And then you can set external force to true and add an external force of 50 Newton on the z direction. If you look at the code, you see that there is a while loop. You here create the sinusoidal reference generation, and then the step reference generation is exercise 2, and then you can uncomment, let's say, the part relative to the exercise to do, and see the result. In essence, here this is the PD controller that is implemented, and you can comment it and see the other PD controller plus gravity compensation, and that's it. And then finally there is the computation of the dynamics, simulation of the forward dynamics, which is in essence inverting the dynamic equation, because we have mq dot plus h equals to tau. So we compute q dot like a minus 1 tau minus h, and then you integrate with over-the-Euler integration to get the velocity and then the position. I don't understand why the visualization is so bad with this. So you managed to enter in the virtual box. You are using Ubuntu 14?
Yeah, but the 18 version.
The 18 version.
Yeah.
I see. Yeah, for the next, I mean, we can continue this lab if you want another time. We try to prepare a virtual box for the 18 version.
Some people are using something called Docker.
Yeah.
So I think it might be easier than the virtual machine.
Yeah. I didn't know how much confident were you in using Docker, so I thought was VirtualBox was easier, but it seems like not. Yeah, because ideally we wanted to make it platform independent. Docker, I think we should do. But if everybody has Ubuntu, it's okay.
Yeah, I have Ubuntu.
Okay. Okay. So I don't know what you prefer to do in this half an hour. If you want me to do this exercise or continue, or if you have more questions.
Maybe can you recap briefly what you've said before?
About what?
Of the lesson in general, like a sort of summary.
Yeah.
Just that we can do the lab next time.
Yeah. Yeah, so in essence, in this lecture we talk about joint motion control for pixel-based robots. We saw that increasing complexity of different controllers from PD to PD plus gravity compensation and PID. And we saw that whenever we go to more than 1 degree of freedom, we have coupling, inertial coupling coming up, and also not only inertial, so centrifugal couplings and Coriolis couplings. And we have matrix that depends on the joint configuration. And we saw that defining, using inverse dynamics, we are able to invert these nonlinear dynamics, joint configuration dependent, and eliminate these couplings, and still close the loop with our desired controller, the centralized one, and achieve a nice tracking even with low gains. While if we have these couplings, we are necessary to need to increase the gains to reduce the influence due to the couplings. Then we found out, we discussed about some limitation of the implementation of this algorithm that are due to non-idealities in the controllers that are depending on the kind of sensor we use, encoders, quantization noise, minimum speed that you can measure, and also we talk about friction forces and how to deal with that, discussing that it's better not to compensate directly but measuring the force of the torques at the link side with a torque sensor or with a force sensor. On the other hand, we had also the backlash problem that can be mitigated through a good mechanical design, and also the dead band that can be inverted in case of hydraulic actuators or electrical power converter, power drivers for the electrical motors. And finally, what was the last one?
Contact folders, no?
Contact.
Gearbox.
Gearbox. The gearbox that allows us, in case of small electrical motors, to amplify the torque at the price of reducing the output velocity, and as a side effect, as the big drawback to increase the inertia of the link, because the inertia of the rotor of the motor is reflected to the link side with the square of the gearbox ratio. And finally, we move to discuss about the dynamics of the manipulator in contact with the environment, showing that the gravitational force it's entering the equation via the Jacobian, and two different ways, the kind of contact that can be established with the environment depending on the kind of contact surface. So if you have a point, we have free contacts, constraints. If you have a flat foot, we have a flat surface. We have 6. We can even have 2 contact points on a line. In this case, we have 6 as well. Each of them is removing 3 degrees of freedom in the matrix. And
In this case, it's 5.
yeah, it's true. The dimension of the Jacobian is 6. The number of rows of the Jacobian is 6, but the rank is 5. Why?
Because moment,
Increasing freedom of the robot.
because we can roll about the 9.
No. Yes. So you here you say you have 3 contact constraints, and you can pivot about this point. But in case you have a line, yes, you
you have one degrees of freedom left, because you can rotate about the line. But you can, in terms of the rows of the Jacobian, you can see this as free rows. So you need three constraints to define this, but to define the second point, you need only two. Okay, because you have this distance and this other let's say in a polar coordinate. You can define the location of that point. So it's only you need only two. That's why the rank of the Jacobian is 5 in this case. Whenever you have 3 feet, so these 3, 2 constraint, this is only 1, because whenever you have 2 feet, the third one is just setting needs only 1 constraint additional. So in 3 points on the ground, you get a rank of 6 in the Jacobian, even if the Jacobian line are 9, because each one foot is adding 3, 3, 3. So you have 12 degrees of freedom, but the rank is 6. And if you have an additional one, the rank doesn't change, so you lose rank 6. But we will discuss about this. We can move forward a bit with talking about redundancy.
One question. Instead of the virtual box on Ubuntu 16, can I launch all the command that you put in the...
Otherwise you can install directly. There is like a possibility to install the libraries in your Ubuntu machine. In the same TXT that tells you how to install the virtual machine, you can directly install all the libraries. There are a bit of things, but this is certainly better. I never tried on Ubuntu 18 how do they look like, because I don't have
Which version of ROS is used?
It's Kinetic.
I think it doesn't work in Ubuntu 18.
Yeah, that's a problem. That's why I came up with the idea of the virtual machine. But we'll see if we manage to.
But then if we install a Docker image, then
It was a matter of time.
One guy did one with a VNC server. So when you start the Docker image, then you can you install a VNC client in your computer, and then you call that VNC server, and it's like you are using VirtualBox.
It's called the server?
VNC.
The VNC server.
Yeah. So it's like the Docker image already has the VNC server to start up when it starts. So you just start the image, and then you open the VNC client to reach that server that is in your computer, and then it goes. That's, I think, good trick.
Okay, we need to understand how to do that.
because in case of installation of the VirtualBox, it's around 10 GB, right? I tried to download the VirtualBox that was available in the Dropbox. It was about 10 GB of space.
Yes.
So I don't know if Docker allows that compromise, it can be less, so that for downloading and things like that.
Yeah, it's better. Yeah, I think the Docker image will be just the size of the code itself. That one, I think there was some space,
No, I think
data space.
Yeah, it's just a matter of downloading.
Yeah,
It
no,
takes a
no.
lot of time.
No, actually, I should have gone like that. I just thought.
I have an image, probably I can give it to you in Docker, and then you can check it for the,
I can install my stuff, yeah?
and then you can see if it's works. It's about a process that I'm doing. So you see that here the Docker, and then after you open this the client, and then you close your own computer, and then you have this. So you can do that.
This is 16.
I don't know. I can check here. I don't know the first one.
Nothing there.
Where I'll move to version if you want to.
LSB release or something like that.
Yeah, I don't know where.
On the Terminator, if you write.
Control-T and LSB underscore release.
What?
LSB underscore release.
SSD underscore
LSB.
B underscore.
Release. I think so.
But this one has for it's inertia.
Okay, carbon edge, LSP.
He found something important.
That's the
16.4.
Ah, that's great.
Yeah.
That's great. Yes.
So probably I can share with you the link where he's
Yeah.
sharing this thing.
Can you write how to use that?
Yeah, he has the. I will send it by email to you.
Okay, that's great. Cool.
So probably we just need to install some stuff here.
Okay,
I'll send it to
very
you.
nice.
Yeah, this up.
Yes.
I don't know if you want to go start operational space control.
We can also stop here.
Yeah, we can stop. I think it's better to stop here and we prepare. We try to make it work this lab next time, and we do more. If you are okay.
Yeah.
Okay. We put this online, like the video. You take care of this.
Yeah.
Thank
Okay.
you so much for
And then-
recording.
Okay. Please give me feedback, really, about everything. It's important to improve.